And the next example, this is something closer to what Jordan showed us. We have this vector, or this, remember, those are curves described by a vector. And what we need to do is three things actually. Find first the derivative vector, and then we need to sketch r at t equals 1 and r prime at t equals 1. In this one I want to show you how to do it on the graph program. Okay, the solution goes like this. Remember, what is the derivative of square root? 1 over 2 square root. And here we have simply minus j. So the first part was instantaneous, and now we need to sketch. So this is where I'm going to change the screen, and I'm going to, well, before I change the screen, let's evaluate. R of 1 is simply I plus 2j. Let's see, R plus j, I plus j, R of 1, right? Plug square root of 1 and then 2 minus 1, and R prime at 1 is 1/2 I minus j. So what do we take from here? How, if I want to graph this vector and write it in a standard notation, what will be the vector? Well, the position vector always starts at the origin, right? You'll see that won't be the case here for our prime. Our prime, if you remember Jordan sketch, we start with the secant and we make the difference between the 2 points closer and closer until we get to the tangent. But r by itself is the position vector. So we can say that the slope in this case will be 1, because you have the j value and the I value are both 1. So delta y over delta x is 1. So we have the line y equals x. On the other hand, here we have the slope will be -1 for j divided by 1/2 for I, so it will be -2. Okay, and now we can write the equation y equals, the point is, if you look at the point is 1 when r equals, when t equals 1, you have I plus j, or the point is xy going to be simply 1, 1. Okay, so the point is y equals 1 minus 2 times x minus 1, or it will be -2 plus -2x plus 3. So having done this, we pretty much know what we look for. So let's put it on the graph program and see what happens. So I lost the shortcut to the graph program. If somebody did some update, but let me switch also your screen. All right. So the way to enter two-dimensional vectors or curves, you insert the function, and to expedite the graphing, enter it as parametric, because essentially you have a function of t. So what is x? Well, x is square root of t. So we'll type x equals square root of t, and y was 2 minus t. So write 2 minus t, and hopefully you can see it on the screen, and graph it, and we let t go from, let's say, 0 to something, to 10 in this case, and there it is. Okay, so you use the parametric. Now the point, we know that the point is 1, 1, so might as well stick it in there. Let's show the coordinate. Okay, so let's show it above right. It's okay. So there it is. So how we show the vector? You see, this particular point has a vector representation, and we already realized that the vector representation is y equal x, because if you look at the note, r prime at 1 is simply I plus j. So I plus j, in this case, we can enter a function which will be simply y equals x. And let's see, change the color, we'll make this red. And we want to let it go from, let's say, the argument rate will go, I want to stop at 1, 1. Okay. So we'll go from 0 to 1. I think this will be the job for us. Okay. We really don't have to stop at 0 to 1, but this is the vector. If we go a little further, we'll have that vector. What about the tangent? Well, the tangent, we have an equation for it, negative 2x plus 3. But remember, this is the graph program. Remember how we were able to enter a tangent to a standard function? Well, it turned out that we can enter a tangent to a parametric. You see, I selected the parametric equation and go right there and insert a tangent, and we need to tell it at what value. Well, we did it at t equals 1, remember? So, and there you have it. And if you look at the equation right there, I don't know if you can see it. Let me bring the legend and make the legend larger so you can see. The graph program figured this out for us. You see negative 2x plus 3. It's there. So this is how it looks like with the graph program. To complete, here's what we learned from this thing. On the xy plane, the curve started. What happened at t equals 0? At t equals 0, you have 0 and then 2j. So the curve starts right here at 0, 2. And the curve goes like this, down, and at t equals 1, we have the point 1, 1 with the two vectors. The position vector of r is this one. So this will be the vector r of 1. And then we have the tangent vector. One question for you guys. Are they perpendicular to each other? The answer is no. The answer is no. They don't have to be perpendicular to each other, because if they are perpendicular to each other, then the radius of the curvature is at the origin, but the radius of the curvature is not. I mean, what's true is that the tangent and the normal are always perpendicular to each other. Turn out in this case that the normal is a different curve. Is a different vector. It's not lining up. This will be the normal, a vector that is normal to the curve. Going back to the graph program, you can see it very well, because we have the ability to enter a normal. Okay, so let's select the function. The answer to your question, Jake, is yes. Normal is perpendicular to the tangent, rather. So here we go. Remember, we selected the parametric equation, and here you have insert tangent slash normal. I'll do that. Oh, I didn't switch the screen, sorry. Okay, again, select, let's move this back here. select the function, and this doesn't matter if it's parametric or standard function. You go right here and enter the same way we entered the tangent. And here we select normal. Okay, let me change color. So what color we haven't used yet? The blue. Okay, and at t, we need to tell it that what is the value of the parameter, and there you see. Now, this doesn't look perpendicular because I need to zoom square, as you guys need to do it on the graphing calculator. And now you see that the purple or magenta and the blue are perpendicular to each other, but the red, which is the vector, the position vector, is not. Okay? So, somewhere, you see the curvature change on this. This is not a circle, so it's not the same curvature, but there is a radius of curvature in the center of curvature or focus, and that varies from point to point. It's going to be, when t equals 1, it's going to be something somewhere on the blue line.